recorded. All right, so this is a lecture on the method of least squares. I can almost read the slides in the mirror in the back in flipped order. So I'm going to see if I could actually lecture by looking at that. I actually got an email today from, I think it was Google, that said, yet again, my top downloaded paper for the week is the notes I wrote on the method of least squares when I was a postdoc at Brown over a decade ago. So I'm not sure if I should be happy or sad about this, but it's good timing. So what I like about this lecture is it gives us an idea of what we can do with all the various things we've been looking at in probability. All right, and it's focused on the screen. Excellent. All right, so introduction. So here is some data points, and it says spring test. It's not the weather and trying to see what the weather is. Who here has taken physics? All right, so what does this represent from physics? I'm sorry, Hooke's law. That, if you look at the force on a spring, the force is proportional to the displacement. This is F equals kx, x is the displacement, and k is the spring constant. And so what I have here is I have a bunch of data points that I just simulated. Okay? I'm a purist. I don't want to go down to the lab and actually measure things. I'll just make up some data. Does the data look reasonable? Yeah, it's not perfect. There's some fluctuations, but it generally looks like a line. If you look at this, what would you estimate the slope is? I hear 1, I hear 4, 5. How are you getting 5?
Dividing the total rise by the total run.
So we go up to 20, come up to about here, go up to like there. It looks like it's about 100. So it looks like it's going up 100 over 20. So it looks like the slope should be about 5. What about the intercept? What would you guess the intercept is? Yeah? You sure it's 0? You sure it's not like a half or?
Well, 0 is the only sensible answer because if I'm displacing a spring 0 meters, I'm going to get 0 force.
So if we believe that this is Hooke's law, then 0 is a reasonable answer. But whether or not the data suggests that, which are you more comfortable with? The 5 or the 0?
The 5.
The 5. Which do you think is the more important number, the 5 or the 0? Yes?
The 0.
Why the 0?
Because the 5 might change from like spring to spring, but if like 0 displacement means 0 force, that should be true for everything.
Okay, so one thing is that if there's a physical law going on, it should, the constant should always be 0. Let's say that this is the only spring we care about in the universe. So we're not going to go from spring to spring. But I want to try to predict what's going on for large x. Which value do you think I care more about measuring? The slope or the intercept? Which is going to have more of an impact on trying to figure out the behavior? The slope. If I'm off by 1/10 in the intercept, it's going to be a fixed error. If I'm off by 1/10 in the slope, then as x gets larger and larger and larger, the error is going to grow from that. So of the two quantities, I care a little bit more about the measurement of the slope. All right, so I actually drew the data from xn is 5 plus 0.2n. Those were my choices for x. My choices for yn were 5 times xn plus an error randomly drawn from a normal distribution with mean 0 and standard deviation 4. And so if it was perfect, if it was y equals kx, k would be 5 in this problem. And I put some Gaussian noise in. I am doing the best fit line, and we'll talk a little bit about the different best fit lines. This is giving a best fit line of y equals 4.99 plus 0.48. Okay? And so a is about 4.99, very close to our 5. But the best fit line it's giving us here has an intercept of about a half. Now the problem is I haven't told you yet how we're doing these best fit lines. So looking at this and going from physical grounds, we're a little concerned about getting this value of b of about 0.48. The 4.99 I'm pretty happy with. That's doing a good job. The 0.48, not so much. How should we measure error? What are some ways we might measure error? No thoughts on how we could measure error? Yes.
As a percentage of like the value you get.
So one thing is we could do percentage of the value we get. But I want a simpler formula than that, though. And it doesn't have to be a good way to measure error. It could be a really bad way to measure error.
X minus
Yeah, a minus observed x.
yeah.
So we could take our predicted value and we could subtract our observed value. And that's probably the simplest way to measure error. How much are you off? What's the problem with that?
Like, whether your error is positive or negative then depends on which way you're off. So you could get a hypothetical situation in which you have a lot of error, but if like your errors cancel perfectly,
Yes.
the error is technically zero.
Yes. This is like the joke of the statistician whose legs are in the oven and upper body is outside in the cold. On average, they're fine. Right? You don't want errors canceling like that. You know, if you have a lot of bad observations, so instead of using just the error, what could we use that would avoid that problem? What's the simplest correction? Simplest is absolute values. And I think we've talked a little bit about why absolute values are bad. What can't we do if we're looking with absolute values? What do we lose? Yes?
Calculus?
We lose calculus. Right? You've all spent, I think, 3 semesters at least learning calculus. It would be really nice to use some of that. So we want a quantity that will not be positive and negative. We want it to only be positive or 0. And we want calculus to be available. This is why we use squares for errors. What else could you have used? Yes?
Any even power?
Yeah, any even power. You could have even taken 4 times the square plus 12 times the 4th power. You could have even done something strange like that. You know, anything like that will work. The square is the simplest thing we can use that is still going to be amenable to calculus. The problem with squaring is now small errors, 2 or 3 small errors count a lot less than 1 medium error. And so this allows 1 or 2 data points to have a profound impact on what's going on. You can do all this analysis. You can find the best fit line using absolute values instead of using squares. But then you can't use calculus to write down a closed form expression for it, and it's a lot harder. All right, so if we use absolute values, then we get the best fit value of A is 5.03, and the best fit value of B is less than 10 to the negative 10. So using the absolute values does a much better job. But it's a lot harder to find these best fit lines. We will actually derive closed form expressions for these best fit lines very soon. Okay. And so just talking about the difference between the method, it's really, for us, B is where the difference is, not the slope A, which is good because it's the slope that's the more important one. All right. So now I'm going to pause on Zipf's law for a little bit. Okay, and I'm going to try to get back to the blackboard. Okay. And is it too high or is it?
It's fine.
Excellent. Okay, if it's fine, beautiful. Okay. So what I want to do now is I want to model a way to describe best fit lines. Now the problem with this is we're finding the best fit line, so we're finding linear relations. Are most relations in the world linear? Give me an example of a nonlinear relation. Physics, economics, chemistry, anything. I'm sorry? Okay. I have no idea what that is, but okay. Do you know what the formula is?
It's a sigmoidal curve, so I don't know.
Oh, is it something sinusoidal?
Yeah.
Great, perfect. And in fact, if you look at temperatures, temperatures are mostly not linear. Maybe if we go to Antarctica, it would be approximately linear. But we have nice seasons here. What's another example? Population growth. If you have a bacteria and it starts expanding, that will be exponential. You have gravity. It's proportional to 1 over the distance squared between them. So I'm going to spend a lot of time being excited about finding the best fit line. Most relations are not linear. Fortunately, it's very easy to move from the best fit line to the best fit of a variety of things. There's a way to linearize things. Okay? And we'll see that later today. We're going to start with the best fit line using the method of least squares, and then we'll see how this applies to other things. So method of least squares. All right. So at xi, we observe yi, I is in 1 to n. And we'll assume all the xi are distinct. This is not a horrible assumption. What this means is I'm not going to do repeated measurements. So if I want to figure out how does a ball roll down an inclined plane as a function of the angle, I'm not going to do multiple measurements at the same angle. I'm going to just choose a bunch of different angles and use that to collect my data. Okay? For a lot of things, it's not unreasonable to assume we're doing things many different times. The problem is, if I have two x's that are the same, unless I get exactly the same value, there's going to be now an inconsistency. If there is a formula that perfectly predicts what goes on, if I have two values of x that are the same, and I don't have the same two values of y coming out, I'm not going to be able, there's going to be an issue. So does everyone agree that this is not that big of an assumption to assume the xi's are distinct? Okay, so there are three types of errors. The first error, error 1, as a function of ab, is going to be the sum, I equals 1 to n, of yi minus a xi plus b. The second one, error 2, ab, was the sum, I goes from 1 to n, I'm using capital N, sorry, of yi minus a xi plus b, absolute value. And then the last one, and I'll write it over here, E3 of AB is the sum, I equals 1 to n, of yi minus a xi plus b squared. Okay. And so we talked about why this is the best one. This allows us to use calculus. Here, for E1, errors can cancel, and for E2, calculus is not available. If I am hiring someone, I actually want them to use E2. If I'm the one being hired, I like to use E3. Okay? So what we want to do is we want to find the best fit line to our data. So we want to find the values of A and B that make this error as small as possible. How can we find the values of A and B that make this as small as possible? What should we do? Differentiate. So we want to take the gradient of E3 and set that equal to 0, 0. Or more explicitly, dE3 dA equals dE3 dB equals 0. Do I have to worry about boundary conditions? We've talked about this before. I've run into the wall before. It hurts. Do I need to do that again? Is it possible that the best fit values of A and B will be at the boundary?
Because the boundaries are negative infinity and infinity.
Yeah, the boundaries for each one are negative infinity to infinity. And you can see, as you let A get larger and larger and larger, as you let B get larger and larger and larger, the fit's going to get worse and worse and worse. You've got some data that lives in a finite region of space. If you send A and B to infinity, you can make your measurements really bad. So I'm not worried about boundary points. All we have to do now is take the derivatives, set them equal to 0, and solve. What class do you think is going to be useful for this? Multivariable calculus will be useful for taking the derivatives, and then to solve, what will be useful? Linear. This is one of the few times where the answer is not real analysis this semester. Right? This is one of the few reasons why linear algebra is a prerequisite for this class. The whole point of linear algebra is to solve systems of equations. We're going to get systems of equations. The important thing in linear algebra is what type of equations are you looking at? It's not a subtle subject, by the way. Linear, right? Linear algebra, not surprisingly, is concerned with studying linear systems of equations. Is this linear? But when we take the derivative, it's going to be linear in a and b. And that's what matters. It doesn't have to be linear in the x's. It doesn't have to be linear in the y's. Those are not variables. Those are observations. It only has to be linear in the parameters. So will be linear in a and b. Okay, so let's come over here. And so now let's take it. So DE3 dA. It's a finite sum. I'm not that worried. So I'm going to get 2 sum I goes from 1 to n. All of this is in the book. So if you don't want to go through and just write the algebra, it's all in the book. This is a really easy lecture for me to prepare because I just have to stand on the board and do a bunch of algebra now. Okay? So I take the derivative. I get I goes from 1 to n. I've got yi minus axi minus b. And now I have to take the derivative of this with respect to a. What do I get when I take the derivative with respect to a? What do I get? Negative xi. So I'm going to put the negative sign over here, and I'll put the xi over here. Okay? And this has to be 0. I can then have DE3 dB. It's very similar. It's going to be negative 2 sum I goes from 1 to n, yi minus axi minus b. But now it was just a 1. Right? Because when I take the derivative of this with respect to b, it's just a negative 1. I've pulled the negatives out. The first step of the algebra is fairly straightforward. Get rid of the negative 2's. Right? Next step, let's multiply in the xi's. Okay? And then what we'll get is the sum I goes from 1 to n of xi yi minus axi squared minus bxi equals 0. And we'll get the sum I goes from 1 to n. This is still in range? Excellent. Yi minus axi minus b equals 0. So I want to write this in matrix form. So something times AB equals something. So when we look at this, I'm going to bring all this stuff over to the other side. And the first component is going to be the sum of xi yi. So sum xi yi. What's the second one going to be? So the top is going to be the sum of xi yi when I bring this over. When I bring this over, what am I going to get? It'll just be sum of yi. Now let's look. I have an a times the sum of xi squared plus a b times the sum of xi. So the first one over here is the sum of xi squared, and this is the sum of xi. All I'm doing is I'm just writing this in matrix form. For this one over here, I'll have the sum of xi, and then I'll have the sum of 1. Yes? I'm sorry? Because I'm moving all these to the other side. Yep. And I can just drop the negative 2's. So we have a matrix. And so if you have, m times AB equals, say, CD, then this implies AB is M inverse times CD. We've got the best fit values. Wonderful. Everything good? Everybody comfortable with the algebra? Anybody concerned about anything? Yes?
What's the determinant of a matrix 0?
Okay, so what if the determinant of m is 0? That would be bad. Like Ghostbusters bad, end of life as we know it, total Platonic reversal. It would be horrible, right? Do we have to worry about m being not invertible? Yes, we're mathematicians. Do you think m is invertible? What do you think? Do you think there might be a condition here that I might have harped on that might be saving the day? Probably the xi's all being distinct is probably going to be very useful and help save the day. Okay? So we're assuming all the x's are distinct. Let's see what the consequence of that is. So how do you tell if a matrix is invertible? You take the determinant. Okay? So the determinant of m, actually, so we'll make this a lemma. M is invertible if the xi are distinct. It actually turns out we do not need the xi to be distinct. A weaker condition suffices. And as we go through the proof, we'll actually see what that weaker condition is. As long as you don't do something incredibly stupid, the matrix will be invertible. There's only really one thing you can do. So if anybody wants to try to be incredibly stupid, what's the one thing that would break everything down? Yes, 1 point. So let's say I want to see how y changes as I change x, and I don't change x. I keep observing y at the same value of x every single time, and I use that to try to figure out how y depends on x with only one value of x. Garbage in, garbage out. You should not be able to make any predictions about how y varies with x if all of your x values are the same. As long as you don't do that, it will work. So you can actually replace if it takes on 2 values. So it's invertible if xi has at least 2 values. So as long as we have at least 2 values, we're fine. So here's the proof. The determinant of m, who remembers how you calculate the determinant of a 2 by 2 matrix? You can do it with hands if you want. Okay, there you go. So it's, if it's alpha, beta, gamma, delta, it's alpha, delta minus beta, gamma. So it's going to be the sum I goes from 1 to n of xi squared times the sum I goes from 1 to n of 1 minus the sum I goes from 1 to n of xi, the sum I goes from 1 to n of xi. All right, now it's time to do some pattern recognition. Does this look like anything you've seen? Does this look like anything familiar? What? It looks a lot like the variance. And if this is looking like the variance, what should this term look like over here? Like the expected value of x squared. So if I want the expected value of x, what should I be multiplying this by? 1 over n. So let's just multiply everything by 1 over n squared. So the determinant of m divided by n squared is going to be the sum I goes from 1 to n of 1 over n xi squared. Now what's the sum I goes from 1 to n of 1? N, and then I'm dividing by an n squared, so I keep one of the n's here, and the other one's is just a 1. And over here, I'll have a sum I goes from 1 to n of 1 over n xi squared. Now, if we interpret the x's as a discrete outcome space, and I put on a uniform probability distribution where each x is observed with probability 1 over n, this becomes the expected value of x squared minus the expected value of x squared, or the variance of x, which is not 0. If some of the x's are repeated, then it's just not a uniform distribution. And I'm just weighting that value appropriately. So as long as the variance is not 0, the matrix will be invertible. And the only way the variance is 0 is if I take every single point to be the same. So we do have to check and make sure that the matrix is invertible, but fortunately it's a very easy check. There is a limit to how much algebra you want to see me do on the blackboard. I think we've reached that. I can actually go through this, and you can write down the formula for the inverse of a 2 by 2 matrix, and then go through and figure out explicit closed form expressions for A and B. I'm not going to do that. That's in the book. You can look that up. Okay? What I want to talk about now is generalizations. Okay? There's a lot of different ways we could generalize this. The first is, what if we wanted to find the best fit parabola? Okay? If we want to find, can I erase the variance argument? Everybody good on the variance? Okay. So there's a lot of different ways to generalize. So the first is if I try to have more complicated functions, so what if I did like, y minus, and I'll change notation a little bit. Let's do it, an x to the n plus an minus 1 x to the n minus 1 plus a0. And then I look at the sum, and this should all be xi's. I goes from 1 to big N squared. It's now highly nonlinear in the x's, but I don't care. I only care, is it linear in the unknown parameters, the a0, a1, a2, an. And when I take the derivative, the 2 plops down, and this is now just a linear expression in my unknowns. And then when I take the derivative with respect to al, I'm going to just get the corresponding thing over here. So the same type of matrix thing will work out, and you'll get some monster matrix times a0, n is equal to something like this. No change at all. So it doesn't have to be a line. In fact, you could go further. I can replace this. I can call this fn of xi plus an minus 1 fn minus 1 of xi plus f1, I guess, a1 f1 of xi. I can put in any functions I want, linear combinations of functions. The important thing is these functions can be as complicated as you want so long as they're known. What must be true is it must be a linear combination of these unknown functions. Okay. So I have a degree in physics. I do like to occasionally use it. So let's go to force for gravity. For gravity, the force between two objects is the product of their masses. You have some universal constant g, and then it's r to the negative 2. What do you think the most important number in this equation is? Yes? Negative 2. The fact that it varies inversely with the square of the distance of separation. There's a beautiful geometric argument as to why this could be true. It's not a proof, but if you imagine a sphere, what's the surface area of the sphere proportional to? Yes? The radius squared. It's actually 4 pi r squared, but it's proportional to the radius squared. If you imagine that there's something in the center that's the source of the force that has a yankage, if the total yankage should be constant as you go further and further out. And what you can say is, how much should it be dropping as you go so that the total yankage over a giant sphere is the same if it's far out as if it's nearby? If the force drops like 1 over r squared, the surface area is growing like r squared, they'll perfectly balance, and they'll all feel the same total yankage. This is not a proof, but it's a nice heuristic argument as to why you might expect gravity to be like -2. So let's say we don't know this constant. And so we will put some unknown number c. And we want to figure out what c is. So we take a lot of observations, we observe what the force is, and we observe what the separation is. And we'll assume that the masses of the objects are not changing. We'll assume the gravitational constant is constant. May not be constant, actually, but we'll assume so. Can we use the method of least squares to find the best value c? Do we have a linear relation in the unknown parameter c? Yes or no? So is this linear in C? No. So we can't use the method of least squares. What could we do to look at a related problem where the method of least squares will be applicable? Yes?
Could you take the log?
Absolutely, right? When in doubt, just say take a log or linear algebra or real analysis. One of those will probably make me happy. Why should we take a log? When you have r to the c, that's indicating a multiplication is going on. There's a product. Whenever there is a product, Pavlovian response, you should think take logs. So now we get the log of f equals c log of r plus the log of g m1 m2. Here's your y. Here's your a, x. I'm sorry. Was I calling this b before? Doesn't really matter. There's your ax plus b. And now you can apply the method of least squares to find the best fit values of a and b. So it applies to more than just linear relations. And this is why we often do things with log-log plots or log semi-log plots. Because if you adjust the data appropriately, you can often reduce something to a linear relation. Now, when we now have to take the log of our force, we now have to take the log of our distance. I don't care. It's just a number, right? It's just the value of the xi that we're feeding in. I don't care if I'm feeding in the radius or the log of the radius. It's a fixed number. So one of your homework problems is actually a homework problem worth doing. It's on Kepler's third law. All right, who knows Kepler's first law of planetary motion? This is what led the great Newton to figure out what gravity was. So Kepler has 3 laws. Anybody want to say Kepler's first law? I think first law is the, yes?
I don't know the order of them, but I know them.
Okay.
One of them is ellipses.
I think ellipses is number 1.
One period goes like a cubed for semi-major.
All right, that's the third law.
The second one is same area swept out.
Yes, equal areas and equal times is the second, I believe. And the third law is the period. I think it's like the square of the period is proportional to the cube of the semi-major axis of the ellipse. And if you just listen to them, this is Sesame Street, one of these laws is not like the other. One of them seems a lot more complicated. Why is it squares and cubes? What's coming on there? And so the homework problem was written many, many years ago, back when Pluto was a planet. So I believe I've kept Pluto in the homework problem. I actually give you the periods of the planets and their semi-major axes and ask you to figure out what the best fit value would be of that constant. And you can actually see Kepler's third law coming from the data. Okay? It's a problem worth doing. And these were big clues to help Newton in coming up with his formula for what gravity should be. Okay? So I hope this gives you some sense of why we care about stuff like this. All right. So I want to shift to showing you some data, and then we'll play a game for homework exemption. Okay, am I back in focus? All right, yes? All right. So here is Zipf's law. So here are the 25 most populous cities from a couple of years ago. Okay? Bunch of values. And I'm plotting the rank of the city versus its population. Which city is the Most populous, second most populous, third most populous. Can anybody give me the functional form of that curve? Yes. So maybe it's a negative exponential. Maybe it's, what else could it be? Yes.
It could be parabolic.
Could be parabolic, maybe more hyperbolic, maybe some kind of power law, maybe r to the negative 3 or something. It's not clear what the relationship is. But if I do a plot of the rank versus the log of population, this is a semi-log plot, it's still not clear. But if I do a log-log plot, what kind of shape does that look like? A line. I understand straight lines really well. If I can, I try to reduce everything to a straight line. And then I can go backwards. And so here's a plot of the 100 most populous cities, probably taken from Wikipedia. I should really write things better. If we do a log-log plot and do the best fit line, it's pretty good. This is looking at rank versus occurrences for word counts. And then this is looking at a plot of the log of the rank versus the log of the occurrences. So looking at how popular certain words are. Okay? What do you think is controlling the popularity of words? Yes? The syntax of the language. So do you think the same word is going to win in different languages? Do you think the same word is going to win over time? Methinks thou art correct. Right? Do you think the same words will win on, say, the Williams campus as the Amherst campus? No. We have much higher quality words, I think, right? What about books versus movies? Or music? Right? So it can depend greatly on the situation. But in so many different phenomena, they're often governed by rules which, if you do a log-log transformation, become linear. And then the method of least squares can be used to figure out the best stuff. All right, I need a volunteer. All right. Now, do you want to know what you're volunteering for, or you're just...
Going blind.
You're going blind.
Yeah.
You are the team captain.
Sounds good.
All right, so it's you guys versus me.
Right.
The goal is to get the 10 most popular words from the site I'm using in the English language. If you can get 8 of them before 3 strikes, we'll play Family Feud style, you all have 1 homework exemption problem in the bank. As team captain,
Sounds good.
you get 2 if you win.
All right.
But if your team loses, you owe me an extra homework problem.
I'll do it.
I'll do it. All right. All right, do you want to turn off the video?